And then in the second talk, coming to how interactions between cells directly can start affecting what one sees, as well as an interesting phase diagram between the adhesivity and the elasticity of the substrate. And the substrate is also a topic of the third talk, where the nonlinearity, where cells can, in certain cases, even affect the elasticity they see and want to thrive in by using this local nonlinearity. We also had some modeling in terms of the motion, and motion trying to be understood in terms of large-scale and collective phenomena, and also how motion is coupled to properties of the substrate, and in the final talk how the migration of cells is also affected by the addition of another organism. There were quite a few questions during the course of the talks, but I'm sure there should be many more, and I think some of the discussions weren't quite completed.
So we heard a lot of different mechanisms. I guess I was wondering what you think the relative importance of adhesion, like initiation of adhesion sites versus sort of the long-term stability of mature adhesions versus regulation of protrusion and modulating all these properties that I've observed in terms of cell stiffness sensing and collective migration.
To whom are you directed?
I don't know.
So I'm sorry, Margaret, actually really sorry that I missed your talk yesterday because it seems relevant to this question. So we actually did a study a couple years ago where we looked at how focal adhesion formation correlates with traction generation during spreading. And one of the conclusions we came to is that before we see any real marked focal adhesion formation or stress fibers, we still see traction generation. And our conclusion wasn't that focal adhesions don't need to be there, it's that we more have to redefine what we define as an adhesion. Yeah. And stop. Too many people look at focal adhesions and then say, it has to be there, and that's the thing linking the cell to the surface and generating force. And then they use these classical markers and say, that has to be the definition. And I think the one piece that we might be missing is just perhaps that the definition of these early adhesions isn't something we haven't clearly defined yet. And Paul had some nice images of, I think it was Vigilin, right, on soft substrates with turf versus stiff substrates, and how transient they are, and how they're much more, they have much more movement and things like this. So I don't have an answer to your question except to say that I hope we can keep redefining it and not get stuck in sort of the more classical definitions of these words.
So you say that cell can migrate, faster than those focal adhesions are formed. Or what? So it migrates, before it attaches out to the substrate.
Well, a cell needs to adhere to move unless it's swimming, right? So it has to have some traction against it. But it's important to remember that some of the most motile cells have very weak adhesions to the surface. Like neutrophil tractions are much smaller than fibroblast tractions, and they move quite fast. So again, we shouldn't make the mistake of saying higher forces equals more migratory or something like that, because that's not necessarily the case. And then in terms of focal adhesions, I think 5 years ago people sort of assume, again I'm getting older, it's probably more like 8 years now, assume that larger focal adhesions equal more force, right? Bigger is better. And I think what we're slowly coming to is that that's not the case at all, that some of the more nascent focal adhesions, or adhesions I should say, are the stronger force generators. And then the actual composition of those, what the turnover looks like, what's in an adhesion that's exerting higher forces versus a more mature adhesion, I don't think that's been as defined yet.
have a general question. Yes. So we heard several talks about interaction of cells with the substrate, and there are very nice experimental data on how the forces are developing between the cells and the substrate. But I don't know, I'm not very familiar with this, but it seems to me that it's more of the sort of laboratory type of thing. It may be more relevant for the actual organism when the cells are interacting and moving not on some kind of a substrate, but on among other cells. And this is, you can view it as like an active substrate maybe, or just interaction between the cells and forces which are developing between cells. I don't know if there is any thoughts about this kind of studies. I haven't seen much of that. And there was a little bit on this, but not.
I think that's true. Many cell types do contact other cells rather than an extracellular matrix. But mostly cells like epithelial cells, what they feel on the bottom is always a little thin membrane of extracellular matrix. So there's often a sandwich in between one cell layer and the other that keeps them separate. And it's often that material, for example, in the kidney or the liver, diseases often arise when that material becomes stiffer. And I think people have only begun to look at, so you can make a mimic of one of these soft materials that looks like a gigantic cell, because the adhesion receptors, I think Cindy mentioned them already, the adherents, the things that mediate cell-cell junctions rather than cell matrix junctions, those things can also be artificially attached to these gels. So you can study cell adhesion to surfaces that mimic the cell-cell contact, and there's very much less of that. And I should mention, working with one of my collaborators at Yasha Kresh, we've just started to look at to put cadherins on these soft materials and to grow muscle cells on them. And the surprising thing is that the mechanosensitive response of the cell to materials that are coated with cadherins looks surprisingly similar to their response to extracellular matrix. And that's a surprising thing, because the whole linkage to the cytoskeleton and the signaling pathways are different. But both of them are exquisitely sensitive to stiffness. And I also wonder whether in some of these cell sorting things, whether in addition to the cell, to the effective kind of surface tension that cells feel, they're also recognize whether their neighbor is stiffer than they are or softer than they are.
It's true.
And, yeah.
That's true. I mean, there's been some recent work that shows that for example, if you press on a cell with an AFM, or if you pull on a cell with an AFM, that both of those are important for determining what the surface tension is. One actually might argue that the surface tension, which is something like an energy, might be a combination of both the adhesive component of that interaction and the repulsive component of that interaction. So I think that's certainly true, and actually I think that was an interesting question, about these ideas of how cells interact through adhesions, but you also might think about how they interact through their cortical net tension or their some elastic property of the cells themselves.
I guess, so I think part of that explanation was that there are two-dimensional layers in the body, right? And that they do exist on membranes. But there is a tremendous amount of effort by lots of people to do three-dimensional versions of all of these things we've talked about. And even on a single cell level, it's tremendously hard, and I haven't seen anybody do it well yet. I mean, no, sorry, they all do it well, but we don't yet have that one Grand Slam canonical example. We all go, whoa, that's it, and it's just because it's so damn hard. And so, imagine doing that, but then adding more cells. I think it's being done, but it's hard.
I'd like to just make one quick question, actually, is that we've been talking about the things like the Young's modulus as being sort of how the cells might interact with their cells, but I'm also wondering if the distribution of forces the active forces within cells. I mean, a big difference between cells crawling on cells and cells crawling on substrate, even if that substrate looks like a cell and has the adhesion to the cell, is that there's active processes and sort of force networks going on in that other cell that could be interacting with. And so I'm just curious, does anybody, are people thinking about that sort of the time-varying interactions that could occur between cells that are alive?
You mean, are people trying to study cells on active surfaces?
For example. Or what else is sort of, that just being a paradigm of something we haven't done yet?
I'm aware of some people trying to use polynipam and actively modulate, stiffness and expansion surface properties to mimic an active surface. But,
So Paul, so if you say that coherence have this stiffness sensing property, then why does Cynthia see that when she puts cells on, stiffer matrices or, regulate the cell ECM substrate, why don't the coherence just get stronger and allow the cells to hold on more?
Yeah, that's it's a really puzzling question. So we were talking about this yesterday. So one of the examples we found that might be related to this is if you have a sparse population of cells, and I think this works with endothelial cells, but it certainly works with fibroblasts. So if you put them on a soft matrix where they're round and amorphous when they're single cells because they're sitting on a soft matrix, when two cells happen to touch and make good contacts, so fibroblasts when they touch will stay together, those two cells will suddenly develop stress fibers and spread as though they're sitting on something rigid. But it's only those two guys when they're touching. Everything else is still round. So the cell-cell contact, maybe because now they're feeling an active partner which is pulling on them as hard as they are, and they may be stiffening themselves while they have that person or that cell person. Friend to pull on. They are different, and I think it has not been possible to differentiate the chemical signals that come from that new class of transmembrane proteins. They signal differently, whether that's the important thing or whether it's now because they feel a different mechanical interface. But I think in all those cases, if you have both classes of contacts, cell-cell contacts, which are variable and alive, and cell matrix contacts, where the bottom part is passive, you still get information from both of those things. And it's unclear how those two systems talk to each other. I guess that's the case. It does not seem that one completely overwhelms the other. They are, right, talking.
So you're saying the different, if you could put integrins on an active surface, you might see similar responses. And so you think the difference may be just the fact that it's an active, so putting coherence on a passive substrate makes them act like integrin-based adhesion.
Yeah, it's possible. I believe that if you put I think people have done this. If you put fibronectin on a very soft substrate where the cell's around, and then you pull on that gel, the cell thinks it's on something stiffer. It responds as though it's on something stiffer.
So I was just wondering when cells put out a Trujan or Philophodia, I noticed somebody showed there was this inhomogeneity in the stresses and the forces. But is the leading edge, or the further you go out, is there a greater force there than if you don't go out so far? Is there sort of a stronger force as you?
When you say go out?
Well, the further out it reaches, or if I look at one protrusion, would I see a gradient in the force where the strongest force would be at the leading edge and less force, so closer into the cell body?
So exactly. So if you were looking at a cell extension, the highest force is at the edge, and it's sort of a gradient inward, decreasing. Though you posed another question which I don't know the answer to, which is, let's say we are able to compare pseudopodial extensions of a given cell of different lengths, whether or not a longer extension would have either a steeper gradient force or a higher force at the edge than a smaller pseudopodial extension. I don't offhand know the answer to that.
Actually, I have a question for you. It's regarding the, it's another line of species. What we have observed for endothelial cells, the traction decreases as the rigidity increases, right? And for one of the experiments, for example, in Korea Institute, they have also measured the traction, but on a micropillar substrate. So do you think substrate structure can play an important role in this? Like how you measuring your force, your tool of measurement can play a role in this case? Or my second question is whether you have tried to do the experiment with fibroblast. So is that it depends on the same type or it's a generic nature? Because it can give us a very different direction to think about.
Okay, so so as far as measurement technique, whether or not there's a difference in traction measurements based on the technique or the platform the cells are sitting on, that's probably a little bit more of an opinion question. So I would venture to say the people who use one platform versus another would say there is no difference, right? Because cells don't live on pillars in the body, but they also don't live on flat surfaces in the body. So, it's hard to say whether or not that translates into force differences. I can say a while back when we were first starting these measurements, we looked at the order of magnitude that we saw in cells compared to measurements Mike Sheets had done using microfabricated cantilevers and experiments Christian's lab had done with the post. And they're all different cells, but they're all in the same order of magnitude for a given compliance. And this was the first time we had measured changes in compliance, the effect of changes in compliance on the traction force of endothelial cells. To my knowledge, I don't know that anyone else has looked at that. We have looked at it in epithelial cells, and we see the inverse relationship that we see with endothelial cells. And other people have taken this measurement with other cell types, and they typically see increased force with an increased stiffness. And that's why we find our result very surprising. And so clearly, at least it appears to be cell type specific. But this goes back perhaps to a little bit what Paul was talking about when you're talking about the native environment that cells sit in and how they respond, quote unquote, optimally given the environment they're used to and sitting in versus the environment that you actually give them. I don't know if I answered your question except to say that I do think it's cell type specific. I don't think we should make broad-reaching statements saying all cells do this in response to stiffness, including generate force. And as far as comparing it across techniques, we haven't physically done it, but I can tell you looking in the literature that I don't know that I would expect it to change.
I think in general everybody kind of says, yeah, method by method, you get kind of the same stuff. I think the big points of contention are the models, like, tensegrity or whatever, like that's where people have knockdown, drag out fights. But I think over whether, putting them on pillars or on surfaces, to each his own.
So a number of the talks talked about sort of cells sensing another one through the substrate. And I was wondering in those experiments, how thick is the substrate? And sort of, you mentioned sort of maybe thin layers, so how does that affect sort of their ability to sense another cell far away? Maybe further than the thickness of the substrate.
Yeah, that's tough. I think those people who worked on these gels have sort of struggled with this to convince ourselves that the thing is stiff enough to be modeled as a semi-infinite, material. And we know from tracking beads that the strain field is undetectable before you get to the bottom of the gel. And we know from AFM measurements that the gels are stiff enough so if you take a spherical probe and push down and use, for example, a Hertz relay, this most naive Hertz relation to measure the elastic modulus, you get exactly the same number that you get from conventional rheometry. So we're not feeling the substrate. We don't propagate the strain field all the way through the gel. with deformations that are in the same order that the cell applies to them when it shears the surface. It is an interesting question how thin you can make it and still be able to do that experiment. That limit seems to be about a micron or so. So unfortunately for things like turf, you can't do these measurements, I don't think, on materials that are thinner than a couple of microns. But typically they're hundreds of microns. But when the cell is pulling them, hundreds of microns on the top, or if you take like in your experiments, when you have something that's a couple thousand Pascal and the cell is putting tens of kilopascal stress on it, it's locally deforming that thing a lot. And that does raise kind of an interesting question of how close we are to being able to use any kind of continuum elastic simple model for these things. I don't actually know the answer to that.
Actually, in Dennis Fisher's group, they are doing the experiment that how deep cell senses by varying the thickness, as far as I was told.
Yeah.
So, yeah.
In fact, there have been a couple of publications establishing new methods that get rid of the semi-infinite approximation. And the one I showed you with the huge island, they found that they had to get rid of that and account for the thickness and say that at 100 microns, which is 100 microns thick, that boundary is fixed and that the cells can feel it. But keep in mind the difference. This is an island that is a millimeter or two across, and the thickness is only 100 microns. So I think you compare the dimensions, and in that case, you certainly have to account for that, and you can't approximate the semi-infinite. But when there's a single cell and it's not a millimeter across, then maybe it's still a good approximation.
Are there no other points for discussion? Well, let's thank our 6 speakers again for but on behalf of all of those people who enjoyed this conference from behind the scenes, I'd like to thank Christina Marchetti, Joe Henderson, and Laura Welch for the lovely organization, and also Penny Davis for the behind-the-scenes work. Thank you very much.
Well, I just wanted to actually thank the few speakers that are left, I should say, and everybody who has come and participated in this. I think it has been a great conference. I don't think we have succeeded deciding what active matter is, but I think we have certainly concluded that there are many, many different things that qualify, from flocks of sheep to tissues today. So it has been really wonderful. And I also would like to thank my fellow co-organizer, Jan Schwartz, who is up there, and Jay Henderson from Chemical Engineering, Roy Welch, who I think has skipped out, but most of all, Parna Bhaskaranan, please, because she has really been the one that has all the work here. I think I can thank. And although most of them have left, I also would like to thank the crew who's been doing the webcasting and working at the camera, all the students, some of them are here, and Samson Pierre, who is our demonstration person in the physics building and has made this possible. And this, I'm personally very grateful, especially for this, because they will actually give me a chance to actually listen to all of the talks that I missed, because I've been interrupted too often with various other things. So thank you to all of you, and I was actually hoping Penny and Don, who were sitting at the registration desk, I told them to step in at this time, but they didn't. I wanted to thank them, because they have also done a lot of work and helped a lot. And one more thing, we really should thank I2CHEM, which is this institute, International Institute for Complex Adaptive Matter, who has really been the main sponsor of this conference. And and especially Dan Cox, maybe he's watching right now, who is at UC Davis and was hoping actually to come, but he couldn't come at the last minute. So let's thank them. And if you do not know what I2CHEM is, I do encourage you to go on the website and find out. You may actually find out that your university is actually a branch or member of I2CHEM, and you may not know. And maybe you can actually organize one of these next year. So please let's give a round of applause to Dan Cox and to Ken.